let's get on with the lecture. Okay, so some of the topics we'll do is we'll start off by defining center of gravity, conditions for equilibrium. So the two conditions for equilibrium, as we saw for extended objects, is the sum of the forces need to be 0 and the torques of these forces need to add up to 0. Okay, again, a whole course statics will be based on just these two equations. Okay, and then we'll look at rigid bodies, object in equilibrium, and then we talk about elasticity of the elastic properties of materials. So we'll define stress, strain, and elastic moduli. The three different elastic moduli: Young's modulus, bulk modulus, and shear modulus. So we'll talk about those three moduli. And elasticity is when you remove the stress, if the object returns to its original shape, then it's exhibiting elastic behavior. And some objects won't return to their original shape, and they're exhibiting plasticity. Okay. All right, so those are the topics we'll cover. Okay, so let's define the center of gravity of an object. So let's say here's a large object. Imagine you break up the large object into little pieces. The force and gravity on this object is there. The force of gravity is in that direction. And all these forces are toward the center of the earth. The force on this is there. Now, all these forces, okay, can be effectively be replaced by this single force, the force of gravity on the entire object, that is the mass of the entire object times its gravity, acting at this point. Okay, so all these forces can be replaced by this single force acting at this point, and this point is called the center of gravity. Okay, so if you have a small object, so for example, if you have a small object of uniform dimensions, the center of gravity is just the geometric center. Okay, and that's where the weight of the object will act. Okay. So we had defined the center of mass of an object as so if you've broken up this object into various pieces, and x1, y1 are the coordinates of this. So this is a two-dimensional object. X1, y1 coordinate, x1, y1 are the coordinates of this mass. X2, y2 is the coordinate of this mass. So the x center of mass was defined as m1, x1 plus m2, x2, and so on, divided by the total mass. Similarly, y center of mass was defined as m1, y1, m2, y2, and so on. Okay, divided by the total mass. So that was the center of mass coordinate of the object. The center of gravity is defined as m1, g1. G1 is acceleration due to gravity there. G2 is acceleration due to gravity there. G3 is acceleration due to gravity there. And that would be the center of gravity. Now, if this object is small, the acceleration due to gravity would be the same everywhere. G would cancel, and this expression would be exactly equal to that. Okay, so what we are saying is for small objects where G does not change over the extent of the object, center of gravity and center of mass are the same. Okay, and that's what we'll be dealing with in most of the cases. Now, for a large, very large object, let's say the size of Mount Everest or something, the center of gravity, this would be slightly different than that. The center of gravity would be lower than the center of mass. Okay, but we as humans, we haven't built structures like that, so we won't worry about that. Okay, so as far as we are concerned, the center of mass and the center of gravity will be the same for all our objects. Okay. Okay. So here's why we'll be interested in that. So we'll be dealing with problems like this. Here's a ladder leaning against a wall, and some of the forces, what we want is for the ladder to be at rest. So we want the ladder to be in equilibrium, and so what we are looking for is these two conditions to be satisfied. The sum of all the forces need to be 0, and the sum of the torques of these forces should be 0. And so the forces on this ladder are, this wall is pushing on the ladder in that direction perpendicular to the wall, assuming this is a frictionless wall. There's a normal force in that direction, and there's a static friction force that's preventing the ladder from sliding. Okay, and there's an additional force of the force of gravity, and we need to know where the force of gravity acts. And the force of gravity acts at the center of gravity, and since this is a small object, that center of gravity is the same as the geometric center of this object. Okay, and so that's why we'll need to know the center of gravity of objects. Okay, all right, so okay, so here's a interesting interesting demonstration. And the cool thing about this is, you can try and do this with Jenga tiles and stuff like that. So you here are objects. In this case, they are of uniform density and the same size and all that. And the neat thing about this is, see, the top tile is beyond the edge of the table. Okay, and the trick to this is the following. Okay, you learn that an object will not topple over as long as its center of gravity is behind the edge. Okay, so this thing will not topple over as long as the center of gravity of this whole thing, which is x 1 2 3 4 5 6 7, there are 7 tiles. This, you see, the center of gravity, the whole thing is behind the edge of the table. Okay, so this whole argument can be applied to each tile. The top tile will not topple over as long as its center of gravity is behind this edge. The top 2 tiles will not topple over as long as their center of gravity of the 2 tiles is behind this edge, and which is true. See, x1 2 is there. The top 3 tiles will not topple over if their center of gravity is behind that edge. Anyway, so you get the idea now. So so you guys should try this with Jenga tiles. Okay, I have a question, so let me pause the recording and I'll answer the question.